Good afternoon, everyone, and thank you for tuning in. Thank you, Georg, for the introduction. Yes, so today I will talk on performance engineering for sparse matrix vector multiplication with the recursive algebraic coloring engine, the so-called RACE library. So the agenda for today's talk is that I set up the stage by briefly introducing SpMV, and then we would do some basic performance modeling for SpMV, and then we will identify the bottleneck or the main bottleneck of SpMV, from which we will derive two optimizations that we will see today, and that is symmetric sparse matrix vector and sparse matrix power kernels. So these two optimizations are not straightforward and include inherent challenges, and therefore we require therefore we use this RACE framework to optimize for these kernels. At the end, we will see some performance numbers as well as some applications that can use this optimized kernels. And so basically, sparse matrix vector is basically doing a multiplication of a sparse matrix A with a dense vector X. And here we see an illustration with a sparse matrix A. And here we multiply it with this input vector X and store or update the result into the vector Y. And the matrix is sparse in the sense most of the elements here are zeros. And therefore, we just store the non-zero entry, which is shown here in red. So such kind of kernel, so matrix vector kernel appear in a lot of fields like quantum physics, quantum chemistry, fluid dynamics, solid mechanics, and the list goes on. And in most of this kernel, most of the time of this kernels or the application is spent in this SpMV routing. And therefore, it makes perfect sense to optimize for SpMV algorithm. And for today's talk, we will stick with the row-based implementation of SpMV algorithm. That is, we use or we compute along rows of the sparse matrix. So we perform a dot product between a row of the matrix and the vector X, so the corresponding elements of the vector X, and store the result into the Y vector. And if we see in the Y vector, we have pretty much linear SSS. So we have cache-friendly linear SSS. And also on the sparse matrix, if we choose a suitable data storage format, we can have linear and cache-friendly SS. But on the X vector, we always require some kind of indirect addressing or irregular SSS. And to this point, I will come again later in this talk. So please remember that in this X vector, we will have some kind of irregular addressing. And so there are many sparse data storage formats to store the matrix A. So the most common one, and I would say gold standard for CPU, is CRS or compressed row storage data storage format, where we store the elements, so the non-zero entries of the matrix A in row-wise. So first we store all the non-zero entries of the first row, then the second row, and so on. And then there are many other data storage formats like coordinate format or LPAC, which are used for GPUs, or hybrid formats like CellC Sigma or CellP, which can be used both for CPU and GPU. But this talk is not going to be about data storage format, and we will stick with a CPU-based implementation. That means we will stick also with CRS data storage format for matrix A, and we will look into node-level implementation of SpMV for large matrices. Large in the sense that the matrix does not fit in cache anymore. So for these kind of matrices, for these kind of large matrices, we can estimate its performance using a simple roofline type approach. And then the performance is given by saturated bandwidth divided by code balance. And saturated bandwidth is something that's dependent on the hardware and can be measured, for example, using benchmarks like stream. On the other hand, the code balance is dependent on the application, and here our application or the kernel is Sparse MatrixVector. So let's see how we can compute the code balance. So bottom left, we see SpMV code written for CRS data storage format. And bottom right, we see the data structures that are required to do this computation. So the first three data structure store the information about the sparse matrix. And the last two are basically storing the vectors y and x. So the minimum data traffic that we require when performing this SpMV routine is when we touch or access all this data structure exactly one time. And code balance is nothing but this minimum data traffic divided by total flops. So that's the minimum code balance. Then so in the numerator, we have the data traffic, and the minimum data traffic is when we touch all these elements once. And here we see there is a component called 12 times NNZ. NNZ is the number of non-zeros. And the 12 comes from the fact that the matrix has to store 8 bytes for the values. So we use double precision, and 4 bytes for the column indices. And that's how we come up with this 12. So 12 bytes is just for storing the matrix A. The rest of the contribution is basically or mainly from the vector y and x. And that's why we have also a dimension of NR. NR is the number of rows. So in the denominator, it is the total number of flops. So if you see the algorithm, we perform 2 flops every non-zero, and therefore we have in total 2 times NNZ flops. Now we can divide the numerator and denominator by NNZ, number of non-zeros, and then we can simplify the equation as shown here. And here the NNZR parameter is nothing but average number of non-zeros per row of the sparse matrix, and is given by NNZ divided by NR. And typically for sparse matrices that we encounter, the NNZR values range from 10 to 100. And in most cases, therefore, the dominant factor of code balance is this factor 12. And therefore, the lower bound for code balance is nothing but 12 by 2, which is 6 bytes per flop. So as the NNZR values increase, we reach close to this 6 bytes per flop lower bound. Of course, here in the algorithm, we right now assume that all the data structure is touched once. And we see in the algorithm this data structure are accessed in a linear manner. However, if we look into the x vector, it's not accessed in a linear manner. And as I said already, we have indirect accesses to the x vector. And therefore, it can be that we need more than one time access to this x vector. So we need to access the x vector more than one time. It could happen. So this depends on the sparsity pattern of the matrix A, as well as the cache size that is available on the hardware. So it's not easy to determine this theoretically. And that's why what we do is we just put a parameter called alpha instead of this 1 divided by NNZR. And so this parameter alpha quantifies this additional traffic for x due to the irregular SSS. Of course, the lower limit of alpha in this case is 1 over NNZR. Now let's see how the code balance that we proposed here, when it comes in combination with the performance model. So performance is given by BS by BC, so saturated bandwidth divided by code balance. And here we see with green line the SpMV performance on one socket of Cascade Lake AP architecture. and which has a saturated bandwidth of 122 gigabytes per second. So the lower bound code balance, which we saw, was 6 bytes per flop. So 122 divided by 6 should give us something around 20 gigaflops per second. 20 gigaflops per second. And we see that even with this naive assumption, we reach, for most of the matrices, we reach close to the estimated performance. And this indicates that most of the traffic comes from the matrix, because the 6 bytes per flop includes only the traffic from the sparse matrix. Of course, now if we include the traffic from the vectors, we could get more nicer or tighter approximation for the performance. And now if we also include the alpha factor, which can be done by using performance counters like Liquid, we can measure the alpha, for example, and then we could get even more closer approximation or estimation for performance. But the takeaway message is most of the data traffic or the performance is dominated by the traffic from the matrix. And therefore, any optimizations on SpMV should first focus on reducing the traffic from the matrix. And in this talk, I will introduce two approaches. One is to exploit the symmetry, and the other one is to use matrix power kernels. So let's go to symmetry. So a lot of problems like computational fluid dynamics or from like quantum physics, they have inherent symmetry in them. That means the matrix that defines the problem will also have symmetry. That means A transpose is equal to A. And this means the lower and upper triangle part of the matrix are similar, or they are exactly the same. So it's just a reflection along the diagonal. Therefore, what we could do is just store the upper or lower triangle part. And therefore, we can reduce the data traffic by a factor of 2. For SpMV with this symmetric matrix, the code is shown here. And now with this illustration, we just store the dark colored or brightly colored elements. Actually, the lower triangle part we do not store, but they are there, but we do not store them explicitly. However, when we perform the SpMV computation, we have to account for this lower triangle part. And this is the reason why we have a new line to our SpMV code. So the second line of our SpMV code accounts for this missing lower triangle part. The first line is exactly similar to what we have in the normal SpMV, and the second line of code just accounts for this missing lower triangle part. And then, yeah, for serial code, it's pretty obvious. You can implement this, and then we could also see an improvement in the code balance. So the code balance for normal SpMV is as seen here, which we have seen before. Now we could reduce it by a factor of up to 2x with symmetric matrix. However, the problem arises when we try to parallelize the code. So now let's assume that we distribute the rows to different threads. And now let's assume we have 2 threads. And so the first thread gets the first 3 rows of the matrix, and the next thread gets the next 3 rows. And if now we start computations, what happens is we could easily see that our results are going to be wrong. The reason is that in the second line of code that we added to account for this missing lower triangle part, we have indirect writes. So that means we write to the vector y depending on the column index. And it can be, as seen here, for example, that both the rows, which are operated by different threads, have the same column indices. For example, here thread 1 has column index 4, and the row on which thread 2 is currently computing also has column index 4. That means both of them will try to write to y of 4. And this will result in write conflict, because if we think of parallel computing, we do not know whether thread 1 or thread 2 has already updated the result on y of 4 in this case. There are many solutions that have been proposed to, or what one could also think of to avoid this problem, like locking. For example, you can lock the output vector and tell, okay, only one thread writes to an element of the y vector at a single time. Or we could use thread local copies, and we could perform the computation on thread local copies and at the end do a reduction. However, these methods work. So these methods work like when you have lower number of threads. However, these are not scalable. When you have like high number of threads, as we have on current multi-core CPUs, where we have 50, 60 cores, these methods are not scalable. Another direction is using specialized data storage format like compressed sparse blocks or recursive sparse blocks. However, here too, we need locks to prevent write conflicts. The other approach is to color the matrix. So coloring has been used to parallelize kernels like Gauss-Seidel or incomplete Cholesky solvers or Cox-Mark solvers, for example. And we could use the same coloring approach to parallelize symmetric SpMV. There are many methods out there to color. And the most prominent one that we see in HPC codes are, for example, multicoloring or algebraic block multicoloring. So algebraic block multicoloring is developed on top of multicoloring and improves the performance of multicoloring. So the benefit of these methods are that we do not need to change the data storage format. Neither do we need locking or thread private vectors. Let's see what happens when you color a matrix. So here we see, for example, symmetric SpMV. In coloring, in multicoloring, what happens is we find rows that do not share the same column indices, and we give them the same color. So here, for example, if we concentrate on the green colored rows, for example, so the second row is the first green colored row, and the second green colored row is the fifth row. So the first row has column indices 1, 2, and 3. But in the second green colored row, we do not have any column indices in 1, 2, and 3. So it has only 4, 5, 6. So this means these do not have any same column indices. And now what we could do is we could permute the matrix or reorder the matrix such that rows with the same color appear consecutively. And now, as these rows do not have or share same column entries, we can parallelize within a color, because now we wouldn't have any write conflicts. However, what we could also observe with this multicolored reordering is that in most cases, what happens is the irregular SSS to the y vector in case of symmetric SpMV would result. So once you SS a color, we would need to load the entire y vector. And for the next color, we would need to load the y vector again. And so if you have more colors, we would need to load repeatedly the y vector. And this can increase our alpha factor and therefore increase our code balance. And this can also be seen by the experiments. For example, here we see performance of, or here data traffic of symmetric SpMV on spin 26 matrix, which has almost 10 million rows. And here the green bar is the data traffic or code balance for the normal sparse matrix vector multiplication. And the roofline model tells we should be around 7 bytes per flop. Okay, we see here like measured 8 bytes per flop, which is okay. And for symmetric SpMV, what we expect is that we expect a lower code balance because we store only half of the matrix. However, what we see here is that the code balance increases than that of SpMV. So if we use symmetric SpMV with multicoloring or algebraic block multicoloring, in this case, the code balance increases than that of SpMV. And consequently, we suffer also in performance. And this was the main motivation of introducing our recursive algebraic coloring engine. And here we addressed this problem. So how to avoid write conflicts and at the same time keep the alpha factor low. And to explain what's happening behind it, here I take a symmetric matrix that is derived from this simple stencil, which is shown here. So, and associated with any symmetric matrix, we can have an undirected graph. Both the matrix and the graph store the same information. For example, the first row of the matrix has column indices 0, 1, and 8. In the graph, we see the vertex 0 is connected to 1 and 8. So both of these actually store the same information. So any operation on a matrix can be directly translated to an operation on graph and vice versa. But for problems like coloring or the race approach that we see in a moment, it's easier to work with the graph. So I stick to this graph approach. And in race, what we first do is find levels of the graph. And this we do by using breadth first search. So using breadth first search or BFS, we find levels. And for this, we start with a root vertex. So let's say 0 and assign it to level 1. Now what we do is now we find direct neighbors that are connected to this root vertex. These are vertices 1 and 8. Now we assign this vertices 1 and 8 to the next level. And then we find the vertices that are connected to level 2, that are 2, 9, and 16, and assign them to level 3, and so on. So basically, we find levels of the graph using breadth first search. So once we find the levels of the graph, we reorder the matrix or the graph according to the levels. So here we have 0, 1, 8, but now we reorder such that now it's renumbered according to the levels. So this makes it easier to work with the levels, and we have continuous access to the levels. So, and also if we look into libraries that implement SpMV, they also do similar kind of permutations to improve the data locality, because these permutations have been known to improve the data locality. So due to the way the levels are defined, we have direct relation or direct connection only with the neighboring levels. That means, for example, if we take level 3, it is directly related only to vertices in level 2 and vertices in level 4. So when updating level 3, if we are computing symmetric SpMV, when we are updating level 3, it means that there are indirect writes or accesses on level 3, level 2, and level 4. And yeah, so it's localized to these levels. It doesn't go outside these levels, the indirect writes. So based on this concept, now we could color these levels. So for this, what we do is we take these levels, we group these levels into 2. So 2 consecutive levels become a level group now, and we color them using 2 colors. So here, red and blue, and we color them like alternatively. First, we start with red, then blue, red, blue, and so on. So if we do it like this, now what we could do is we can compute all the red colored level group in parallel. And now we don't have also any write conflicts, because if we now, let's say, focus on thread 2's level group, there is level 5. So if we have indirect writes on level 5, it will go to level 4. But level 4 is in a blue colored level group. And this is not done by any threads in the current step. It has also dependency to level 6, but level 5 and level 6 is done by the same thread. So there is no write conflicts. Also, level 6 is dependent on level 7, but again, level 7 is in a different level group. So in a different means in a blue colored level group. So no thread is working on it. So once we do all the red level group, then we could switch and do the blue level group. Okay, and in this manner, we do not end up in any write conflicts. So on the graph, it looks like this. So the first two level groups are this bottom left level groups. Then we have blue level group, red, blue, and so on. And now if we distribute threads, so let's say if we are now computing on red level group, there is a problem, because what we see here is, for example, the thread that work on the lower left level group have smaller amount of work compared to a thread that works on the middle portion of this graph. And therefore, there is obvious load imbalance. So in order to get good performance, we have to do some load balancing. And this is implemented in RACE, and RACE takes care that, that all the threads get even amount of work. And if we do this, now we see that we do not disturb any locality of the graph or the matrix to be general. But at the same time, we don't have any write conflicts. And therefore, we observe, when you see, if you measure the data traffic, we can observe that we have a lower data traffic compared to that of multicoloring or algebraic block multicoloring approaches. And the traffic is even lower than that of SpMV. And so this is what we normally expect with symmetric SpMV. And due to the lowered data traffic, we also get an improvement in performance, right? So this is the basic idea of using symmetric with RACE. And this is not just for the spin matrix, which I have shown, and we have shown that this performance improvement can be achieved on a wide variety of matrices, like what we see here. And in most cases, we see RACE as an upper hand in performance. And on an average, on this Skylake CPU, we reach almost an average speed up of 1.6x compared to the best multicoloring approach. If we compare it with MKL, for example, MKL SpMV, we can reach something like 1.4x speed up. So this is basically the optimization with symmetry. And in the next part, I will show you how we can do another kind of optimization called matrix power. So the symmetry optimization, as I said, is problem dependent. That means the matrix has to be symmetric. That is, it has to satisfy A is equal to A transpose. However, the matrix power, it need not have this requirement. So it need not be that A is equal to A transpose. However, it's dependent on the algorithm. So all the algorithms cannot use matrix power. On the other hand, with symmetry, you can use it in all algorithms. So the focus the symmetry optimization was to get parallelism, and get parallelism in a way that we do not end up in right conflicts. However, with matrix power, the focus is not on parallelism, but to cache the matrix entries so that we can get or improve the performance. So now let's see how we optimize for matrix power. So in matrix power, basically we calculate a raised to p times x. So where A is a sparse matrix. And normally in traditional approaches, this calculation is performed by repeatedly performing SpMV computations. So if we have an input vector x, so the input vector x, which is stored in y of 0, we could do SpMV once, then we would get ax, which is stored in y of 1. Then we could do SpMV again to get a squared x. And similarly, we can go on to compute a raised to p x. However, the problem here is like we do the complete SpMV on all rows of the matrix to get ax. So this means, for example, if we look at the matrix, how we update the matrix, which is shown on the right-hand side. And on the left-hand side, we will show the level view. So the levels are the same as that of rays that we have shown. And now if we see how the updates are being done, what we do is we start with the first level or first row of the matrix and continue and do the ax computation for the entire matrix. So once ax is computed for the entire rows, now we start with the computation of a squared x. So when we start the computation of a squared x, we assess the first row of the matrix A, which was already assessed when computing ax. However, when the matrices are large, this entry or this rows of the matrix are no more in cache and therefore has to be loaded from main memory. So every time we assess the matrix, we have to load it from the main memory. So if we perform the computation for a cube x, we have to load the matrix 3 times from main memory. However, if we see the algorithm, we see that the matrix A is same for all the k iterations, right? So the idea is, can we reuse the matrix A? So if we can reuse the matrix A, then the code balance can improve by a factor of p times. And yes, so the answer is yes, we can improve the code balance. And for this, we can use the same level-based concept that is used in rays. So to demonstrate the idea, so here I show the levels again. So the levels are shown with circles. So in the first row, we see the levels when they are updated to ax computation. So when these levels are updated to ax computations, these levels are bright. When in the second row, we show the levels when they are updated to a squared x computation. So right now it's blended. This means we haven't started with the computation of a squared x. So the bright colors means that the computation of the particular ax, for example, here is already done. So in normal method, what we would do is we would first compute ax and then start with a squared x, right? But now again, if we analyze the dependency, we see here in the algorithm, y of k is dependent on y of k minus 1. This means level 1, when computing a squared x on level 1, it's dependent. It has to ensure that ax is computed already on level 1. Okay. And also we have seen we have direct dependency only with the neighbors. And so if we perform SpMV on y of k minus 1, this means the level 1 can have indirect access to the same level, level 1, and also its neighbor, that is level 2. So this is it. So it has only the dependency with level 1 and level 2. This means to update level 1 to a squared x, it needs to ensure that level 1 has been updated to ax and level 2 has been updated to ax. This means the computations on level 3 to 15 for ax is not required at the moment. And therefore, we do not need to pollute the cache by bringing in these elements. And rather, what we do is we reuse the elements that have already been loaded. Similarly, if you go to level 2, so level 2 can be updated to a squared x if level 1, 2, and 3 has already been updated to ax. And in a similar manner, we could also argue, for example, level 1 can be updated to a cube x at this stage because level 1 and 2 has already been updated to a squared x. So we can go in this manner. And what we see here is the levels that are brought up in ax can be reused in quick succession. So then we can reuse the levels. So levels means matrix elements in quick succession. That means we can reuse it from the cache. So on matrix view, this means, so if we start with level 1 computing ax and level 2 computing ax, after level 1 and level 2 has computed ax, what we can do is we can compute a squared x on level 1. So the level 1 that was recently loaded is reused again. And we can go on like this, and we can reuse these elements. And this means we load the matrix A from the main memory only once when computing ax. The rest of the accesses when computing a squared x and a cube x can be served from the cache. And due to this, we can also attain performance improvements or performance speedup because we keep the matrix entries in cache. And this is seen here in this picture. So here we have ordered the matrix from left to right according to their size, so increasing size. And the dotted line represent the cache size of this architecture. So this is Ice Lake CPU with 104 megabyte of total cache. And the matrices towards left of it can fit in cache. And that's also the reason why the matrices on left do not have a high speedup, because the matrix is already in cache. So we do not need extra caching to improve the performance. However, the matrices on the right, we see that we can have huge performance benefit by using this approach of race. So the numbers that we see on top of these orange bars, which represent the performance of race, is the optimal power value that has to be computed to reach this performance. So this means for this matrix, F1 matrix, we need to perform the computation of a raised to 6 times x to reach 50 gigaflops per second in this case. And on an average on this Ice Lake socket, we attain an average speedup of 2x for these large matrices. And of course, if the matrices, or if the caches are fast, or if we have larger cache as that of AMD EPIC Rome CPU, we can have a higher benefit. And here, for example, we reach an average speedup of 3.5x with AMD Rome system. Now, as I said, this matrix power cannot be used for all the applications. So this is application dependent. However, there are classes of applications where we could use this. So one class of application is when we have to compute the matrix polynomial. And for example, the applications under them include like Chebyshev time propagation, exponential integrators, polynomial preconditioning. And the other class of algorithms that can use matrix power is S-step Krylov schemes, like S-step GMRS solver or S-step CG solver. So these are the two applications that I currently found. So there might be other applications also which can use matrix power kernel. So if any one of you has already some applications that you think we can use matrix power, please feel free to contact me. Or even if some applications that use GMRS solvers or polynomial preconditioning, we could try using rays and trying to speed up the performance of these methods or these algorithms. So what I did recently, so recently means like 2 weeks back, was I integrated rays to the Trillinos framework. And Trillinos has already S-step GMRS and polynomial preconditioning. But for this matrix powers, they use repeated SpMV computation. So what I did was with rays, I substituted this matrix power kernel that they have with our rays optimized. So the matrix power kernel that is optimized with rays. So you can reuse the matrix elements in cache. And in the following slide, what we see is the performance improvement that we achieve for S-step GMRS solver when using rays. So on the y-axis, what we see here is the final solve time for two matrices we show here. So the Emilia matrix and Eldor matrix from the suit sparse matrix collection. And the left bar shows the time required to solve them without rays. And the right bar shows the time required to solve them using rays. And for example, on this case, we have a speed up of 1.2x, so 20% saving in time. And what we see here is the red bar that was for SpMV is now substituted with our matrix power kernel from rays, which is this blue. And this requires much less time because of the cache. For Eldor matrix, we have a higher speed up. That's because the proportion of time that the S-step GMRS solver spends on SpMV is higher for Eldor matrix. And since we optimize this SpMV algorithm, the impact is much higher for this Eldor matrix, and that's why we get 40% improvement. For polynomial preconditioning that's used in Trillinos framework, for example, we get even higher speed up. The reason is most of the time in this is spent of this application is spent in the preconditioning, and we can improve the speed of preconditioning because we use the polynomial preconditioning, which inherently use matrix power kernels. So if we substitute with a rays optimized kernel, we could improve the speed by 60% for Emilia matrix. And for Eldor matrix, we get almost up to 85% speed up. Right. So these are the two, so basically these are the current results that I have with Trillinos framework. So what we have seen today is like, we have seen, okay, for sparse MatrixVector, the major data traffic contribution comes from the matrix. And we have seen how to reduce this data traffic contribution from sparse matrix. And we used two methods. One was to exploit symmetry. And the other method is to increase the caching. And we have seen various applications which can use them, and also the performance speedup that we could attain using this method. And for both of these methods, we saw that we could use this race framework to improve the code balance and attain the performance benefit. And we attained performance benefit for symmetric variants, something around 1.5 to 1.8x. And for the matrix power kernel, we could get up to 4x or even higher normally. And it has to be said that in this talk, I just gave a brief idea on how, or the concepts of the race framework. Under the hood, race does much more optimizations like recursion and some grouping of levels and point-to-point synchronizations and stuff like that. And this is how we get these high speedups. And yeah, that's it basically. And thank you for listening, and I'm open for discussions.
Thank you, Christie, for this enlightening talk and the impressive results. Are there any questions? Please raise your hand if you have any question or comment.
I'm not an expert in this subject, but the talk was quite easy to follow. I'm interested to know if some of this also applies to structurally symmetric matrices, that the structure is symmetric, but the matrices are not actually symmetric. That is what happens with all finite element and I guess many other.
Yeah, so if it's structurally symmetric, we can use, but the problem is we have to store the values. So it won't bring much of a benefit because we have to anyway store the values of the matrix, right? But so the symmetry optimizations won't bring in much of a benefit. But of course, if there is an algorithm that in which we can use, for example, matrix power kernels. So if we are using like solvers like GMRS or something, then of course we can have benefits. Yeah, then we can have benefits. True.
Okay. And a second question, if I can.
Yeah.
This was mainly on CPUs, but you expect it to be also extrapolable somehow to GPUs, or they are?
So right now it's not planned. So right now we focused only on CPU-based implementations. Right now I have only looked into CPU-based implementations and how to speed up. So so matrix power kernels, it's easy to extrapolate it in the thinking, for example, to GPUs, because you don't have problems with the parallelization, because in GPUs, you need a lot of parallelization or parallelism. And for matrix power kernels, you don't have this problem. So probably, I think matrix power kernel is, if we start with GPU implementation, it is the first kernel or the optimizations that one should look into, right?
Thank you very much.
I have a question, Christie. Could you probably comment a little bit on what would be the toughest challenges if you want to port some of those ideas to a distributed memory setting?
So for symmetric sparse matrix vector optimization, it's easy because basically what you can do is you can do a symmetry optimization on the local part of the matrix, right? So you can take the local matrix and apply all the optimizations that I have shown here. So and do the node level implementation using something like this, which I have shown. But the challenge happens for matrix power kernels because the problem is, as I said, you have dependency with the neighboring levels. So you have to take this into account also in distributed memory setting. And you have to find, so when computing, for example, a cubex, you have to store at least 3 ghost layers, for example. And then we can do it. And the thing is, it's interesting if we look into the literature. So people have done this distributed memory setting already. So what people haven't done is keeping, or most of the people didn't concentrate on keeping the metrics in the cache. So that's what we did, so the node level. But the distributed memory setting is already done. So we can implement, or we can put this race framework into that, because they have this framework. Like I know one of the developer in Trillinos, for example, had previously worked with it. So for distributed memory setting, they did this to avoid communications between MPI processors. But now we can also on top improve the caching too. So yeah, it's possible, but it's a little more difficult than the symmetry optimizations, I would say.
You would have to introduce ghost elements for the matrix too, but that's not too difficult. It's just a matter of space, because the matrix doesn't change in this algorithm.
Exactly, but the problem is you would have extra computations. You would have to compute for these ghost layers too. Mm-hmm. So if you want to compute a cubex in the ghost layer, in the immediate ghost layer, you have to have a squared x already computed, mm-hmm. and ax. And this means there are some redundant computations. So it depends how big these ghost layers are. So normally, if you have small ghost layers, it doesn't hurt. And it has been shown that it brings in performance improvement. Also, you can reduce the communication between MPI processors in this manner. And this was also the major motivation of introducing such kind of matrix power kernels. Right.
Thanks. Are there any more questions or comments?
Okay, very nice talk. I'm very excited. So it's great work. Christie, what is your plan for the future? Do you plan to write a library with iterative solvers, or you plan? How do you want to expand from here?
So right now, what I have is like this race library. So basically, if you see the race library, it is something like OpenMP, for example, because you have a code, like a symmetric SpMV code you provide, and you just provide this to the race library. Mm-hmm. And the library handles for you the parallelization and the dependencies and stuff like that. So for Trillinos, what I did was I just used the Trillinos. So I just implemented the basic kernels that are required for Trillinos, and I put this into this library. So the library then handles for the parallelization and stuff. So I think this is the best way to go with this also, because you can provide any kernel that you like or which you think there are dependency, and then the library handles the parallelization and all the dirty works, basically, actually. So I think, yeah, this is the, but the challenge is basically, right now, the problem what I see is most of the sparse MatrixVector kernels or BLAS implementations for level 1 and stuff, they do not provide support to compute, for example, on a certain set of rows. So when you call, for example, SpMV, it computes the entire SpMV for the entire rows. So if we have support to compute on a subset of rows, then this is really easy for race. So you can just provide in race this, because race needs to operate on subset of rows, because it's not going from start to end. Because as you see also on caching, it needs to operate on some set of rows and then go back and operate again on some other set of rows. So if we have support to operate on certain set of rows, then so start and end, for example, as an argument to the function, then we are good, actually. Then it's easy to implement with race. So you can just put the function to the race, to provide it to the race library, and then it can do it on its own, basically.
Okay, yeah, thank you very much.